Alright, hey everyone, hope everyone's doing well. The purpose of this video is just to give a brief introduction to multiple regression. And so, multiple regression is just like what we've talked about the first 4 or 5 weeks of this class, simple linear regression, except instead of just using one predictor, we're going to end up using multiple or more than one predictors in our model. To start, we're going to give a couple of motivating examples. And so both have to do with this New York homes data set that we've been looking at. And so just as a reminder, the response that we've been thinking about has been price. And the explanatory in this example, we've kind of looked at a few different predictor variables, but in this case, the predictor is lot size. One possible motivation for using a multiple regression model is if the assumptions for simple linear regression aren't satisfied. For example, here we see that there's some points with pretty high leverage. And when we plot two regression lines, one with the points, one without the points, we see that they're having a fair bit of influence on the slope of this regression line. Before, our solutions were to fit a model with and without these points and present both, or we might try a transformation, but we said problems with transformations were that the resulting coefficients weren't always interpretable, or at least weren't as easily interpretable. And so we might think that adding in another predictor might kind of explain why these points are so influential, and in a multiple regression model, these points would no longer have the influence that they do in this simple linear regression model. A second motivation that we'll just briefly mention is that we saw in some capacity that a confidence interval or a prediction interval for a new response, those intervals might be pretty wide if there's not that strong of a relationship between our response and predictor. Adding more predictors, if those predictors are useful, can kind of narrow the interval. And an example is given here where if we look at a prediction interval for the price of this new home that has a size of 1,200 square feet, the interval is almost useless. It's from -3,000, which is obviously going to be more than 0, to 191,000, which doesn't really tell us very much. I think for most of us, we don't need a ton of motivation for multiple regression. I think it's natural for most people to think of the response being associated with multiple different factors. And so it's natural for us to want to include those factors in a larger regression model that takes into account all of those predictors. Okay. So throughout this section, it's going to be structured in a very similar way in that a lot of times the simple linear regression model is just going to be presented. We're not always going to talk about it. It's just there for reference so that we could compare it to the multiple regression model. And so in this case, we've given our simple linear regression model as well as its assumptions, the fitted model, how those estimates for beta hat naught and beta hat 1 are found using least squares, how to fit the model in R. Again, we're not going to talk about that, but we have it printed here so that we could do kind of a quick comparison. And so really getting going, our multiple regression model, I'm going to start out by just writing part of our simple linear regression model, and all it is just going to expand this to have a lot more predictors. And so we defined in the previous section that P is the number of beta parameters in our model. And because of that, p minus 1 is going to be the number of predictors, because we have our extra parameter, which is our intercept. These errors are going to have the same exact assumptions. So they're going to be independent, and they're also going to be normally distributed with mean 0 and standard deviation sigma squared sub epsilon. Our fitted model then is going to be the model that we estimate from our actual data set. And our beta hats are from minimizing the sum of squared errors. And so you should really kind of notice that this really isn't that different than what we've already talked about, right? It's the same exact thing, same assumptions, same kind of form of the model, except there's some extra predictors, same form of the fitted model, except there's some extra predictors. The beta hats are found the same exact way by minimizing the sum of squared errors, and so that's really the same as well. We don't get a nice picture of this because now there's more than one predictor, and so you're into multiple dimensions, which gets a lot harder to graph, but the same exact concepts hold. In R, you actually also just fit the model in almost the same exact way. The only difference is that we're using plus signs to add these extra predictors in. You'd add as many predictors as you want in your model. Other than that, same exact deal. It's response tilde, the predictors that you're adding up, you give it the name of your data set, you name your model, and you use summary to get a summary of that model. And so aside from those plus signs, this is the same. We mentioned throughout this that working with R should get easier and easier. This is one of the big reasons why. There's not some new thing to learn for multiple regression fitting in R. We're just using the same exact kind of syntax that we used before. But now since we've used it so many times before, it should come a lot easier this time around. All right, so we'll leave it off here. In the next video, we'll start to talk about some interpretations in multiple regression and how those are different from how we've interpreted our coefficients in simple linear regression.